Section 3.7, implicit differentiation. Okay, the logical follow-up to the chain rule. What we're going to do here is, in some sense, differentiate an equation. Maybe more accurately, we're going to differentiate a function determined by an equation, but we may never know exactly what that function is. That function will be given implicitly by an equation. The problem is there's multiple functions implicit to many equations, and many of the equations we'll encounter. Good news is we won't have to actually look for the function itself. We'll be asked more indirect questions. So first, we'll start out by defining what it means for a function to be implicit to an equation. So we're still differentiating functions. They may not be functions we actually have a real tangible grasp of. We only know these functions implicitly. They are implicit to an equation. So what that means is function f of x is implicit to the equation capital F of xy equals 0. So all this means is we've got some equations with x's and y's in it, and numbers and so forth. Or maybe sines and cosines and logarithms and whatever. It's some equation of x and y. Function f of x, lowercase f of x, is implicit to this equation if the substitution y equals f of x into the equation yields an identity. For example, so let's illustrate that and show how we can have multiple functions implicit to a single equation. Consider the equation x squared plus y squared equals 1. It's the unit circle in the Cartesian plane, so here's a picture of it. We want to find functions that are implicit to this equation. There's two hopefully fairly obvious ones and infinitely many more, it turns out. First off, the function f of x equals square root of 1 minus x squared. I might emphasize positive square root of 1 minus x squared. That's implicit to this equation, since if we'll substitute y equals f of x into x squared plus y squared, we get x squared plus f of x, whoops, missing an exponent there, squared. We get x squared plus square root of 1 minus x squared, here's my exponent, squared, which is x squared plus 1 minus x squared. The x squareds cancel, you're left with 1, and we get x squared plus y squared equals 1. So upon substituting in y equals f of x, we get this equation to hold. Therefore, that function f of x is a function implicit to this equation. By the way, what's the graph of this function look like? F of x equals 1 minus x squared square root of. That'd be y coordinates of points on this equation, the graph of this equation, which are non-negative. It'd be the top semicircle. The top half of this circle is what we'd get by taking the positive square root of 1 minus x squared. What if we did this a different way and we took g of x to be the function negative 1 minus x squared square root of? So we'll take the negative of the square root. By the way, the graph of that would be the lower half of this circle, the lower semicircle. Well, you know that's going to be implicit as well, because if we substitute in, then we get x squared plus negative 1 minus x squared square root of squared. Well, that negative sign gets absorbed by the squaring. And we also get 1 out. So substituting in y equals g of x also produces an identity and is also a function implicit to that equation. So there's two functions implicit to that equation. As I commented, the f of x function is the top half of the circle, and a g of x function is the bottom half of the circle. Of course, x squared plus y squared equals 1. That's not the graph of a function. That fails the vertical line test. Both of these pieces of the circle in red, the red parts, they do satisfy the vertical line test. They're functions. They're functions implicit to that equation. In fact, they're the only continuous functions defined on the interval -1 to 1, which are implicit to x squared plus y squared equals 1. But there's other functions implicit to that equation. In fact, there's infinitely many others. The others are discontinuous, though. Here's a couple of them. We could take, as long as we satisfy the vertical line test, we're good to say this is a function implicit to that equation. We could include this point and take this quarter of the circle, include this point, 0, 1. Then we'd have to go down here and exclude that point, and then we could take this quarter of the circle. This stuff in red, I could write out as a piecewise defined function. It's pieces of the f function above and pieces of the g function above. But it satisfies the vertical line test, and this is a function also implicit to the equation x squared plus y squared equals 1. Nothing wrong with that function. It just happens not to be continuous, which would cause some differentiability problems. Remember, differentiable implies continuous, so at discontinuities, we don't have differentiability. But I'm just talking about what it means for functions to be implicit at this stage. Here's another one with the idea being, I could take the top part for a while and stop and jump down to the bottom, make sure if I include a point up here, I exclude the corresponding point down here, and then take the bottom part for a while. If we include a point down here, we got to exclude the corresponding point up here with the same x coordinate to satisfy the vertical line test, and then we take some more. So here's a couple more functions, and I could chop this top part and bottom parts of that circle up just as long as I satisfy the vertical line test and create, however you like, equations, or I'm sorry, create functions which are implicit to the equation x squared plus y squared equals 1. So if you're told y is a function implicit to the equation, however it's expressed, you can't tell what the function is necessarily. I mean, sometimes you can just solve for y in terms of x unambiguously. Other times you have to settle for the fact that y is a function implicit to some equation. So if y equals f of x is implicit to some equation, then we can generate an equation containing dy dx by differentiating implicitly. So what we'll do is we'll differentiate the equation. For example, x squared plus y squared equals 1, we'll differentiate that implicitly with the understanding that y is a function of x. So we'd have a function of x squared, that's a composition of functions of x. That's why we're doing this after the chain rule. How do you differentiate compositions of functions? Using the chain rule. They both start with C, was my little mental catch on remembering that. Since a function's not necessarily uniquely determined by an equation, we may not be able to get an explicit formula for dy dx like we have in the past. That's okay. Maybe the derivative will involve both x and y values, as we'll see. So suppose y equals f of x is a function implicit to the equation x squared plus y squared equals 1. Find dy dx is the plan, and here we have it down here. So we'll have to differentiate implicitly, because what we've got when we say x squared plus y squared equals 1, we've got x squared plus f of x, y equals f of x squared equals 1, and that's a composition of functions of x. Okay, so let's do it, and the goal here is to find dy dx. So we'll differentiate both sides of the equation, x squared plus y squared, and 1, differentiate with respect to x. Usual properties of derivatives, that's the derivative of x squared, plus the derivative with respect to x of y squared. Okay, we won't always take the next step, but this is our first one of these. Right-hand side, still the derivative of 1. Let's substitute for y f of x. So this then becomes a derivative with respect to x of x squared. Piece of cake, we've done lots of that. Derivative with respect to x of this composition, f of x squared. With the composition, it'll require the chain rule. And the right-hand side's easy. Derivative of x squared with respect to x, 2x. Derivative of 1 with respect to x, 0. Derivative of f of x squared, chain rule says, bring that exponent of 2 out front as a coefficient, reduce the exponent by 1 to 1, rewrite the inner function, and then chain rule, multiply by the derivative of the stuff inside. The derivative of f of x is f prime of x. In fact, that's what we're looking for. So that produces this equation here. Maybe I could replace the f prime with a dy dx. So we'll usually work with the differential notation for derivatives, the dy dx stuff. This being our first one, I just want to go ahead and introduce the f of x there. So you very explicitly see a composition of functions. Problem is, you don't know what f of x is. And we've got a composition of functions up here. We've got the squaring function, and inside of that is the function y of x that's implicit to this equation. So we really have a composition in what's highlighted here as well, but this shows it more explicitly. All right, so we've got what, 2x plus 2y dy dx equals 0. I'll hang on to the little arrow in the square brackets for a while, emphasizing that when we differentiate implicitly, we must respect the chain rule. So we'll see lots of little arrows in what follows. And we were looking for dy dx. Okay, so let's take the 2x to the other side as a negative. We'll divide both sides by 2y to get dy dx equals, the 2's cancel, negative x over y. So for a function implicit to the equation, x squared plus y squared equals 1, we get the derivative of such a function to be dy dx equals negative x over y. This is the first time we've seen one where the derivative involves both x's and y's. Yeah, because this is the first time we've differentiated a function that we didn't really exactly know what the function was as well. So I'm not surprised to see some newness in the form of the derivative. If I think of this in terms of maybe lines tangent to a curve, here's the problem. Simply knowing the x value doesn't determine the y value. Remember, x squared plus y squared equals 1. That violates the vertical line test. For a given x value, there's more than one y value. Usually there's two y values. For every x value between -1 and 1, there corresponds two y values. So if we wanted to talk about the slope of a line tangent to the graph of that equation, we got a problem unless you'll tell me both the x and the y coordinates of this point of tangency. We'll do an example to illustrate it, but let's go back up to the graph of x squared plus y squared equals 1. For example, suppose we wanted to find the equation of a line tangent to the graph of x squared plus y squared equals 1. At x equals, let's use square root of 2 over 2, or 1 over the square root of 2. That's the example we're about to do. Problem is, I give you that x value, there's two y values. There's a point up here and a point down here that have that same x value. So a single x value doesn't determine a y value. So if I want to find equations of tangent lines, and that seems to be something I'm inordinately fascinated with in Calculus 1, something to do with rates of change, an x value by itself won't do in this setting. I need an x value and a y value. I can't find the y value just from the x value because this isn't a function. It violates the vertical line test. So let's do exactly that. All right, I'll point out we had just seen that when we differentiate implicitly, x squared plus y squared equals 1, we get dy dx equals negative x over y. So in the next example, they want us to find the slope of the line tangent to x squared plus y squared equals 1 at the point xy equals square root of 2 over 2, comma square root of 2 over 2, and do the same for the point square root of 2 over 2, comma negative square root of 2 over 2, and we'll draw a picture to make sense out of it. So that's what we were just talking about. Let's do that. They just give you the x value square root of 2 over 2. I don't know which y value to use. They got to tell me that as well, because we don't have a function. But we've got functions implicit to these equations. Okay, so here's the question. We need the derivative. Like I said, we just saw that for function y equals f of x implicit to this equation, we have the derivative dy dx equals negative x over y. So if I'm going to use this, I need x values and I need y values. Okay, ed square root of 2 over 2, comma square root of 2 over 2. X and y are both square root of 2 over 2. So we'll take the derivative and evaluate it. Remember, vertical line means evaluated at xy equals square root of 2 over 2, comma square root of 2 over 2. So we'll plug square root of 2 over 2 in for x. So we'll have negative square root of 2 over 2. We'll plug square root of 2 over 2 in for y. So we get an x over y. They're the same, but this is the x value and this is the y value, and there's the negative sign from up here out front. Those cancel, leave us with a slope of -1. We'll draw a picture and see if that makes sense in a little while. So straightforward, you take the derivative and you plug in the information. Just this time around, the derivative is taken implicitly using the chain rule, and the information is more involved than just an x value. It's an x value and a y value. Do it at this other point. Okay, then we'll take the derivative and evaluate it at xy equals square root of 2 over 2, comma negative square root of 2 over 2. Okay, it was negative x over y. Here's the negative out front. Here's the x value, square root of 2 over 2. Here's the y value, negative square root of 2 over 2. The negatives cancel, the numbers cancel, leaves us with a 1. This time the slope of a tangent line is 1. All right, let's draw a picture and see if any of this makes sense. So here's x squared plus y squared equals 1. Here's the point, square root of 2 over 2, comma square root of 2 over 2, and directly under it is the point, square root of 2 over 2, negative square root of 2 over 2. And up here we had a tangent line of slope -1. Down here we have a tangent line of slope 1. And that looks geometrically about right. The reason we chose the square root of 2 over 2 is to get these nice, clean slopes of tangent lines. Yeah, this is slope -1, this is slope 1. You had to know both the x value and the y value. Being told simply x is the square root of 2 over 2 would not tell you what y is. It's ambiguous. There's two corresponding y values. So you got to be told the y value as well. And derivatives in this setting have that same type of interpretation as they did earlier. They're slopes of tangent lines. Slopes of tangent lines, this time to equations, whereas before they were slopes of tangent lines to functions. Well, granted, this time they're functions as well. They're functions implicit to those equations. Let's do a couple more examples. Okay, let's do number 16 and 20. All right, where they just ask us to find derivatives, differentiating implicitly. So we're illustrating the procedure. Find dy dx for y, an implicit function of x given by this equation. E to the x squared y equals 2x plus 2y. Okay, so we'll just differentiate both sides of the equation implicitly with respect to x. Differentiating with respect to x, to be informal, means differentiate the x's like you usually do, and differentiate the y's as if they were functions of x, which, just between you and me, means you differentiate the y's just like they were x's, but then you add a dy dx. It's the chain rule that tells you to add the dy dx. So we'll see some chain rule stuff popping up left and right. Okay, so how do you differentiate? Actually, let's do the right-hand side first. What is the derivative of 2x with respect to x? Same as before. It's 2 times 1. What's the derivative of 2y with respect to x? Remember, y is a function of x. Well, when you differentiate 2 times this function of x, you'll get 2 times the derivative of that function of x. So we get 2 dy dx. So, technical difficulties here. So you treat the x and y differently. That's because you're differentiating with respect to x and y as some function of x. So differentiating 2x, we simply get 2. Differentiating 2y with respect to x, we get 2 dy dx. Let's differentiate the left-hand side. Okay, it's an exponential function with some stuff inside it. Composition of functions, chain rule. So we'll differentiate the exponential function, which really means just rewriting the exponential function, rewriting the stuff inside, and then multiplying by the derivative of the stuff inside. Says who? Little arrow? Chain rule. It's composition of functions. The outer function is the exponential function. The inner function is x squared y, also a function of x. Just I don't know what the y part is. Okay, so we've got x squared, a function of x, times y, a function of x. That's a product of two functions of x. So we'll have to use a product rule. Notice, since y is a function of x, we got to use the product rule in differentiating x squared times y. We'll have the derivative of the first times the second plus the first times the derivative of the second. There's your little picture of the product rule in terms of square brackets. Derivative of x squared with respect to x is 2x, differentiated as usual. Rewrite that second function of x, y, plus the first, x squared. Now we need the derivative of the second. The derivative of y with respect to x is dy dx. So we get a dy dx here, not a 1. We're differentiating with respect to x, and this is not an x. It's a function of x, y equals f of x, if you like. So we get a dy dx when differentiating the second. And the question was dy dx equals what? When you differentiate implicitly, you produce an equation, and it's got a bunch of dy dx's in it. And then you solve for dy dx, and you're good to go. So differentiating implicitly produces this equation. Now we just solve that equation for dy dx. So it's a matter of rearranging things. Let's see, let's clean it up a little bit. And usually when I'm done differentiating, I got square brackets all over the place. I'm proud of myself and my square brackets. But they can be cumbersome if we've got to do additional manipulations, which now we do. All right, so let's see, what do we got here? 2xy, x squared dy dx. You got that exponential stuff out front, right? On the right-hand side, you've got 2 plus 2 times dy dx. Okay, let's distribute on the left-hand side. This is 2xy times the exponential. There, x squared times the exponential times dy dx, x squared times the exponential times dy dx. Right-hand side's in pretty good shape as it is. Let's get all the dy dx stuff on the left-hand side and all the non-dy dx stuff on the right-hand side, and then divide. So let's see, x squared, the exponential, dy dx, there that is. Let's bring this dy dx stuff to the other side. Comes to the other side as a negative. Let's take this stuff, which doesn't have a dy dx in it, to the right-hand side. There it is, it becomes negative. There's that 2, so everything's accounted for. Let's factor a dy dx out of this, so skip that step of algebra. Then we'll have dy dx times this minus 2. Divide both sides by that minus 2, and that produces the formula for dy dx. If you're bothered by the skipped step of algebra, pause the video, write it out, and make sure you believe it. These are kinds of manipulations you would have to do. So once the differentiation is done, once the implicit differentiation is done, it's just a matter of algebra, of rearranging things and solving. For dy dx, it's become the unknown. So there's the derivative of y with respect to x for a function y implicit to this equation. By the way, can you solve for y here? If you can solve for y in terms of x, you don't need this implicit differentiation stuff. There's some of the homework problems in the book where you could rearrange things and express y as a function of x explicitly, and then just differentiate the old-fashioned way. Yeah, that's all well and good. Maybe not the best examples to illustrate implicit differentiation. But can you solve for y here? No, you can't. You've got a y stuck in an exponential function over there. How would you get it out? I could take a logarithm. That'd get it out of that exponential function. Yeah, but then this y on the other side of the equation would be stuck in a log function. So this is one of those where nobody can solve for y in terms of x. It is impossible to solve for y in terms of x in this particular equation. So we'll differentiate implicitly, and there's a derivative, and we're stuck with a derivative that involves both x's and y's. Let's do another one. Consider cosine r plus cotangent theta equals e to the r theta. They say find dr d theta, where r is an implicit function of theta. They're using this r and theta stuff to foreshadow polar coordinates. Maybe you've seen polar coordinates in pre-calculus or high school. You'll see them likely if you take a physics class, you'll see polar coordinates. If you take an astronomy class, orbits of planets are usually addressed in terms of polar coordinates. In Calculus 3, you'll see a lot of that stuff. You'll see polar coordinates and you'll see planets, Kepler's laws addressed in terms of polar coordinates, r's and thetas. So it's common to have r as a function of theta in certain settings. But anyhow, they're really just doing this to give you variables other than x and y. So we've got then r as a function of theta. So here's a composition of functions, one inside the other. The outer function's cosine, and the inner function is r. I don't know what it is explicitly, but r is some function of theta. So we have cosine of r of theta, if you like. We usually don't write the of theta stuff, but when we differentiate this part with respect to theta, we'll differentiate with respect to theta because we're looking for dr d theta. We'll need the chain rule on this part. Here, cotangent theta, you're going to need the chain rule there. No, that's just the cotangent function of theta. Differentiate that with respect to theta. Derivative of cotangent, what was that? All the cofunctions had derivatives that started with a negative sign. It was negative cosecant squared. It's kind of similar. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. I've tried to give you patterns on those. But no, I don't need the chain rule on that one. And here we've definitely got a composition of functions. We'll need the chain rule on that one. Hey, you see that r times theta up there? That'll require the product rule as well. So I'm predicting chain rule, nothing in particular on that one, chain rule and product rule on this one. Okay, so let's differentiate both sides with respect to theta. Why with respect to theta? Why not with respect to r? Because the question is find dr d theta. So differentiate with respect to theta, and some dr d thetas will pop up probably from the chain rule. Okay, what's the derivative of cosine r? Oh, I left a little arrow off, should have a little arrow there. We'll differentiate the outer function. Derivative of cosine is negative sine of r. And then the chain rule says, excuse me, missing a little arrow. The chain rule says multiply by the derivative of the stuff inside. So that produces a dr d theta. Don't forget the dy dx's. Don't forget the dr d thetas. If you leave them off every time, you're going to know you messed up. Because the question is, what is dr d theta? You leave the dr d thetas off, you've produced an equation that, for one thing, it isn't correct. For another, doesn't include any useful information. If you left dr d theta off, you're looking for dr d theta, or dy dx more commonly. But it's a chain rule. We differentiated the outer, we rewrote the inner, and the little arrow should be there, derivative of the inner, symbolically at least. Differentiate cotangent theta, negative cosecant squared theta. Differentiate it with respect to theta. Derivative with respect to theta, it's clearly a function of theta. And derivative of cotangent theta with respect to theta is negative cosecant squared theta. Differentiate the exponential function, which amounts to just rewriting it. It doesn't change when differentiated. Rewrite the inner, the r theta. Chain rule says multiply by the derivative of the inner. Okay. Derivative of r times theta, r being a function of theta. I don't know what it is, but it's given to be given implicitly by that equation. So we've got a product of two functions of theta. One of them's r and the other one's theta. Then we need the product rule. We'll have derivative of the first. What's the derivative of r with respect to theta? I don't know. In fact, that's what I'm looking for. Derivative of the first times the second, plus the first, r, times the derivative of the second. Derivative of theta is 1. Derivative with respect to theta of theta is 1. Right. I hesitantly mention the following in passing. Would you maybe want to treat the derivative of theta with respect to theta as like d theta, d theta? I mean, that is 1, I guess. You want to treat it as d theta, d theta? I can't argue with the validity of that. Just to simplify it and make sure you replace it with a 1. And that gives, I don't know, more of a democratic status amongst r and theta. But they don't play the same roles exactly. R is a function of theta, and we're differentiating with respect to theta. That gives a lopsidedness to the roles the variables play, and they do get treated differently. You differentiate thetas as usual, you differentiate r's as usual, but then you stick a dr d theta on the end. So says a chain rule. So we had to use a product rule. In here you see it. There it is in terms of the square brackets. Let's clean this up a little bit. So we've got negative sine r dr d theta minus cosecant squared equals, let's bring the theta out front. That'll give us a theta e to the r theta dr d theta. Distribute, that gives us an r e to the r theta. Right. As before, let's get the dr d theta stuff on the left and the non-dr d theta stuff on the right. So we'll take this over to the other side of the equation. It'll go as a negative. We'll take this negative cosecant squared theta to the right-hand side. It'll come over as a positive cosecant squared. So on the left-hand side, we'll have a negative sine r dr d theta, a negative theta e to the r theta, negative theta e to the r theta dr d theta, also factored out, skipped a step of algebra. Now let's divide both sides by this coefficient to get dr d theta by itself as this quantity here. It's got both r's and thetas in it. We played a game in the past. Could you solve for r in terms of theta? You couldn't then. I think it's even worse here. Could you solve this for r and do this without implicit differentiation? Well, you'd have to get the r over here out of the cosine function. You'd have to get the r over here out of the exponential function. I'd use a log to get the r out on this side. I'd need a cosine inverse and some amount of luck on the left-hand side. It ain't going to work. Now, if I apply a cosine inverse, I'm happy about this part, but the other stuff is going to be just a mess. If I take a logarithm, I'm happy about this part, and the other stuff is going to be a mess. So no, you can't solve for r in terms of theta. Nobody can. It's one of them unsolvable things. So we're stuck with implicit differentiation, and it's fairly straightforward. You must become comfortable with implicit differentiation. Many of the applications we do, applications coming up in chapter 3 at least, are definitely based on implicit differentiation. See, we did both of those examples. Let's move on to something else, which I think they've postponed until now, talking about a line normal to a curve. We could have done this back when we were talking tangent lines to curves early on. But they put it here. They say a line is normal to a curve at a point if it is perpendicular to the curve's tangent line. The line's called the normal to the curve at that point. So can you tell me how you'd find the slope of a normal to a curve? It's perpendicular to the curve's tangent line. How do you find the slope of a tangent line? Derivatives. Okay, what happens when two lines what happens in terms of slopes for two perpendicular lines? If we want a line perpendicular to a given line, we use negative reciprocals of the slopes. Perpendicular lines have negative reciprocal slopes. So how are you going to find the slope of a normal line? I'll use the negative reciprocal of the tangent line, the negative reciprocal of the derivative. So this is just a little extra nuance on some of the geometry involving curves and the use of derivatives. To inspire this, the book tells the following little story. Suppose we have here, we've got the surface of a lens, a glass lens or eyeball or whatever. We've got some sort of lens made out of, say, glass, and a ray of light comes in and it enters that lens and it's refracted. And the way it's refracted is related to some parameters involving refractivity of air and glass, say, and it's related to angles with angles made with normal lines. So they're using this as justification to talk about normals to a curve. When light enters a lens, the angle that the ray of light makes with a normal line to the lens, so the light's coming in here, here's the lens, the light's going to enter at that point, we'll take a normal line to the lens. How are you going to find that? Using calculus, we'll take a tangent line and do a negative reciprocal thing to find the slope of that normal line, as just discussed. But this is the angle A that they're talking about. And the angle the ray of light makes with the normal line to the lens once the ray's inside the lens, angle B, here's angle B. So it comes in at one angle, that angle's changed. These are related by something called Snell's law. I don't think the book explicitly states this, but this is what Snell's law says. They're related by the formula n sub A sine A equals n sub B sine B, where n sub A is the refractive index of the medium outside the lens, air, I guess, and n sub B is the refractive index of the medium out of which the lens is made. Presumably it's made out of glass, say. So anyhow, there's physical reasons to have an interest in the normal line to a curve. In this case, the curve being the profile of the lens. So you get this kind of bending. Hanging out, you stick your fishing pole in the pond, it appears bent, and that reflects this bending to give you something more tangible. But anywho, there's what the book uses to justify this idea of normals to a curve. Let's illustrate it with a couple of examples. Okay. Some of these are computationally a little tedious. It says, verify that the point pi force pi has is on the curve x sine 2y equals y cosine 2x, and find the equations of the lines that are, part A, tangent to, and part B, normal to, the curve at this point. Okay, first, verify these x and y values satisfy that equation. All right, we'll take xy to be pi force, pi has, and we'll plug them into this equation. X is pi force, so we'll have pi force, sine 2, y is pi halves, equals y pi halves. Cosine 2x is pi force. Let's see, that'd be pi force, and cancel the 2's there, we get a sine pi. Pi halves, we get a cosine of pi halves there. Sine of pi is 0. Cosine of pi halves is also 0. Yeah, we get 0 equals 0, so it is satisfied. Notice I put little question marks over the equal sign. I didn't know they were equal till we got to the end. So it's kind of as if we're asking the question, are these the same? So I mean, not right equals, that assumes what we're trying to show. But we've seen that we do get the equality here. This is true. 0 does equal 0. And so, in fact, that point does lie on that curve for what it's worth. They want us to find the equation of the line tangent to that curve at this point. Okay, we got a point. We need a slope. And we use the point slope formula to find the tangent line. Okay, we'll differentiate that equation with respect to x. We need a dy dx. I can't solve for y. And probably ain't anybody can solve for y in this equation. It's a transcendental equation. So we'll differentiate implicitly. We need dy dx. We'll take dy dx, we'll plug this in for x and that in for y. That'll tell us the slope. And we'll have a slope, we'll have a point, we'll be good to go. So differentiate. Need a product rule here. We'll have derivative of x is 1 with respect to x times sine 2y plus a derivative, derivative of the first times the second plus the first x times the derivative of the second. Now we're going to differentiate sine 2y with respect to x. That's a chain rule. Derivative of sine is cosine, so we get cosine, rewrite the inner, 2y, and multiply by the derivative of the inner. What's the derivative of 2y with respect to x? It's 2 dy dx. Don't forget the dy dx. We're looking for dy dx. Right-hand side, similar manipulation. It's a product rule. Chain rule will be a little bit easier. Let's see, product rule have derivative of y, which is dy dx, times the second, cosine 2x, plus the first, y, times the derivative of the second. Derivative of cosine 2x is negative sine, rewrite the inner, 2x, and multiply by the derivative of the inside. You want to put a dx there? Can't say it's wrong. It clutters things up a little bit, and I wish you wouldn't. But if it helps you remember it by putting 2 dx there, fine. Just simplify it to 1 in the next step, and you'll get this. So we've used a chain rule. Use a chain rule twice, it looks like. So I should be able to look up here and see compositions twice. Yeah, there's a cosine function with a 2 times function inside it. Here's a sine function with a 2y function inside it. The 2y function being more complicated than just the 2x function as functions of x. Okay, so we got this. We'll clean it up a little, so we get sine 2y. Here we've got, say, 2x out front, cosine 2y. There's a dy dx. Cosine 2x dy dx minus 2y. Let's take that to the next slide. So we'll recopy this last line. And we need to solve for dy dx. So we'll get the dy dx stuff on one side, the non-dy dx stuff on the other side. That'll produce, after factoring this equation, I encourage you to pause and make sure you believe all of this. Let me speed up the algebra a little bit. Factor on the left-hand side, divide, and we get dy dx is this thing here. Okay, so there's dy dx. What are we looking for? Tangent line to the curve at this point. Okay, we got the point, we got the derivative. All we got to do is plug the coordinates of the point into the derivative. I got to use the coordinates, the x and the y this time because of the implicit differentiation stuff. So we'll plug x is pi fourths, y is pi halves into the derivative. That is, we'll take the derivative and evaluate it at xy equals pi fourths, comma pi halves. That'll give the slope of the tangent line. All right, x is pi fourths, so we'll get a pi fourths there, there, and there, 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 and there. And then we get the pi halves in the appropriate positions. Let me speed things up a little bit. We get a slope of 2. Okay, so the tangent line has slope 2 and passes through the point pi fourths pi halves. So let's use the point slope formula, as we usually do with derivatives, because we get a point from information they give us, and we get a slope from derivatives. So point slope formula, here we have a slope of 2 from this, 2. We've got the point x is pi fourths, so we'll take x minus, say, x1 pi fourths, y minus y1, say pi halves. Simplify, looks like we get y equals 2x. That looks awfully easy. It's got the right slope. Does that really pass through this point? If I plug in x equals pi fourths, we'll get 2 times pi fourths. Yeah, that is y equals pi halves. It actually does contain the point, just double checking. So there's the equation of the line tangent to the graph of that equation at the given point. Part B, normal to the curve. How are you going to change things? Let's see, normal to the curve means perpendicular to the tangent line. Tangent line has slope 2. We need a line that's perpendicular to a line with slope 2. That's a line with slope -1/2. To find the slope of a perpendicular line, you take a negative reciprocal. in this case, a negative reciprocal of 2, giving us a slope of -1/2 for the normal line. So now we've got the slope -1/2, and we still got the point pi force pi has. This part actually fairly easy once we had already done the tangent line stuff. So we've got a slope, we've got a point. We'll use the point slope formula, and this time this is what we get for the perpendicular line to the graph of that equation at the given point. Slope's -1/2 on this one, slope was 2 on the other. Multiply those together, 2 times -1/2, -1. Yeah, they're negative reciprocals of each other, as desired. Let's do one more.